Yuan Zhang, a first-year PhD student in University of Melbourne. This is a pre-recorded presentation for the 2021 meeting of the Australasian Mathematical Psychology Conference. The topic of my research is comparing planning algorithm with humans on the Tower of Learning task. This work is supervised by Dr. Neil Levitsky and Professor Charles Kemp. My talk will be in three parts. In the first part, I will introduce some motivation of the study. In the next part, some related background will be provided, including previous literature on computational models of human problem solving and some basic knowledge of AI planning algorithm. In the final part, I will describe the experiment and our results, also the possible future directions. Current study in the field of human problem solving mostly focus on domain-specific problem solving, while people demonstrate impressive performance on new tasks, which is also known as analogical problem solving. This phenomenon implies humans should have some general mechanism to deal with complex tasks. Basically, the big problem I want to solve is if we can build a general cognitive model for human problem solving. And why I think AI planning algorithm can be helpful to understand this general mechanism. First, AI planning community has developed many general planners, which can be used to solve different tasks as human did. Secondly, planning algorithm use a state space model to represent the problem and forward search algorithm to explore the problem, which is also very similar to how humans represent a task and solve the task. Last but not least, most planners use the general model-driven heuristics. This component might explain why humans can deal with new tasks. So here, we just narrowed down that big problem, a general cognitive model for human problem solving, into a smaller problem. Can we find a general planner to simulate the human behavior? Here, I want to note that we are not using modern state-of-the-art planners, but rather components from these state-of-the-art planners and composing simpler planners that lend themselves better to this type of study. As state-of-the-art planners have too many components that it would be hard to identify which are the key factors and which are the confounding factors. Okay, so now let's talk about the background. Actually, the idea of using program to simulate human cognitive process can be traced back to the general problem solver by Neville and Simon. However, this approach has been pursued less actively from the mid-1990s, but there are two recent progresses make this approach worth revisiting. Firstly, from the mid-1990s, modern planning algorithms have relied on domain general heuristics that can be derived automatically from a problem. This approach to deriving heuristics could potentially lead to new models of human problem solving that can be applied to broad families of problems without requiring problem-specific strategies, as we mentioned in our motivation. Secondly, psychologists have continued to collect behavioral data on problem-solving tasks, and some of these data provide new targets that computational models can aim to capture. In recent years, more advanced computational models have been explored, which Mars Lab used a tree search model with a domain-specific heuristic to predict human performance on a two-player game. Carl derived a meta-level Markov decision process model to simulate human behavior on a more slab task within the framework of resources rationality. It is worth to note that most recent studies use non-deterministic environments so that humans cannot easily derive an optimal solution. And there has been relatively little work on deterministic environments in recent years, and this is what we want to do. And the next, I will provide some basic knowledge on AI planning. Planning is the model-based approach to reasoning about the actions needed to achieve a goal given an initial scenario. In the worst case, planning problems are computational intractable. Hence, AI researchers have focused on developing new research algorithms and inference methods to scale up to larger problems, as well as trading off solutions time for plan quality, also known as the satisfying approach, which is also believed to be the possible underlying mechanism of human problem solving. And first is the classic planners. Classic planners are originally designed for deterministic and fully observable tasks. Two classic search algorithms, breadth first search and depth first search, constitute the most basic blind classical planners. But blind classical planners have no information about which state is closer to the goal, and hence the order in which they explore the space of solutions is independent of the goal, which is not very efficient. By contrast, AI researchers have focused on planning as heuristic search. A heuristic planner usually consists of two components: a search algorithm, just like breadth first search or depth first search, but they also has a heuristic function derived automatically from the symbolic description of the problem, such as goal counting heuristic, which simply means the number of goals that are not being achieved yet. So this heuristic function can lead the planner to decide which state might be closer to the goal. Since the later 90s, heuristic planning has been the dominant approach to solving deterministic tasks. But when dealing with complex tasks with limited reasoning time, it is sometimes impractical to find the pool plan as what classic plans did. So online planners are proposed to deal with this scenario. Unlike classic planners, online planners do not aim to find a full plan from the start state, but rather focus on choosing which single action should be executed at the current state. A prominent approach to online planning is mental culture research, which has achieved impressive success at playing Go. And this kind of planner has also been explored as a model of human problem solving in like Wijma and Slab's work and some other works. Okay, so now let's so now let's jump into the task we used in this work. It is actually a variant of Tower of Hanoi. We use the Tower of London task. Basically, the goal in Tower of London task is from the we need to move the boards from the start configuration to the start state to the goal state, and also like this from the start state to goal state, and this is the A and the B are two different instances, and there are some constraints. First, we can only move one ball at a time, and second, we can never exceed the hit limitation of a pick. Like here, this in this configuration, each pick has the hit limitation of 1, 2, 3 respectively. Okay, so why we use this task? First, there are comprehensive studies by the psychologists on this task, so we can use many previous behavior observations to verify our idea. Secondly, the task itself is a deterministic and a single-player task. It is also a natural playground for classic planners. Moreover, it is very similar to the Block's word domain, which is a very popular domain studied by the planning community and compared to traveling sales program. No visual cue can be used in this Tower of London task, which means the participants cannot rely on their intuition to solve the problem. They have to do some abstract reasoning, which is more useful for us to observe the general planning method. Okay, so now the question is, how can we compare the planning algorithm and human performance on this task? As cognitive process is usually unobservable, normally we can only identify which model is used by human when they predict different behaviors. However, in the simple task like Tower of London, most AI planners can generate the optimal plan or almost the optimal plan, and so the human. So it is impossible to distinguish between different models and determine which model fits the human cognitive process. So here we use an novel indirect approach to compare them. As mentioned previously, Tower of London task has been extensively studied by psychologists, and several structural parameters have been identified that affect the difficulty of the instance for humans. So we simply explore the extent to which the performance of the AI planner is influenced by these structural parameters. And we use the number of generated nodes before first action to denote the preparation time needed for each planner. And this is a list of 5 structure parameters we used, and it is also used in Berger's study, and the behavior results are also come from their paper. I just leave this page as a reference. Okay, so this page shows the result of our experiment. Regression coefficients summarizing the influence of 5 structure parameters on model planning time. It's the first 8 columns, and human planning speed, the second last column, and human solution speed, the last column. And here we just focus on the comparing the first 8 columns with the second last column, human planning time. And each cell shows a standard beta value orbited from a regression model. Deep red means the p-value associated with a coefficient is less than 0.001. And the light red means the coefficient means the p-value is larger than 0.001 and less than 0.05. Coefficients in white cells are like here are not statistically significant. Okay, so and here are the most important message we can obtain from the table. First, we can see here none of the planners match the human data in full, but A star with goal counting and breadth first search both capture the effect of the 2 parameters with the biggest influence on human planning time, minimum moves and start hierarchy. In addition, online planners can capture the effect of start hierarchy very well. We can see the numbers. This is a human planning time behavior data, and this is online planner. They can capture the effect of start hierarchy pressures. So here we just use 2 different heuristics. ARM-CUT is a popular heuristic that allows AI planners to perform well on challenger problems. But we find that a simple goal counting heuristic yields more human-like performance than ARM-CUT does. Although ARM-CUT is more informative than goal counting, the goal counting heuristic is easier to compute, which could explain why it might be more natural for human to use. When combined with the goal counting heuristic, the optimal planner A star accounts better for human performance than the satisfying planner this greedy algorithm, which suggests that people are able to go beyond a simple greedy search strategy on this simple task. And our results suggest some clear directions for future work. Developing a computational model that can account for the influence of all 5 parameters on both planning speed and solution speed is a clear challenge for future work. And it seems possible that a hybrid approach that combines online planning with classic planning will be able to address this challenge. And we will also need to investigate new general heuristic from the AI planning literature as we intended to scale up to different and larger problems. So goal counting might not be possible for this kind of problem. A second direction for future work is to apply computational models directly to the behavioral data in a way that allows for individual difference. The regression analysis we reported and by Berger provide a simple initial target for computational modeling, but working directly with the data that they collect would allow a more fine-grained model evaluation. That's all of my talk. Thank you.